So last week we considered the case of omega being some subset of r squared with gives, so these define x and y are right, are defined properly defined using this, right, and right, a joint the idea is probabilities to regions, right. Some region D is what we used last week. Okay, it doesn't matter. So you do this double integration like this. Note that, right, D can be any arbitrary region in R squared actually, because we are right, we are going to define, so fxy is defined for all R squared by domain extension, although it is non-zero, it is 0 outside not in omega. So this is just a summary of what we saw last Wednesday, in last Wednesday's class. We have taken an integrable function, two arguments fxy, and we are defining it over the whole plane by domain extension, like we did for this one the PDFs of one variable. Here, right, we have a region, a well defined region where x and y take values, which is, right, a uncountable subset of R squared. Now there is a small notational extension I have to do. What if my x and y are obtained from a bigger space, for example some r power k for k bigger than 2, right? In such a case we would have to, we can you cannot claim that omega itself is contained in R squared. Omega can be bigger, but x and y are two continuous random variables, right, and I mean they are just two random variables, so they have to take values only in the plane together. So for bigger omega, i.e. in that is omega, let us say, is a subset of some r power k, k more than 2, we still we can still have two continuous random variables x and y. Only thing is, right, you will have to qualify, right, the subset in which they take values. So you define omega xy as the subset of R squared where x and y take values, right, or in which jointly take values, that is also important. Now this omega xy notation we have already seen in the case of discrete, right. The same idea, except that it is now an uncountable subset of R squared as opposed to a countable subset that we had earlier, isn't it. So I just want to right, from now on, since we are only going to for the time being focus on two random variables x and y, we can stick to omega xy rather than, we should realize that right, it is unfair to call omega xy as omega. Omega can be much bigger. You could have a random vector with umpteen components and you can just focus on two of them, in which case you would need something more specific. So that is all. So this notation omega xy is exactly the same whether we deal with two discrete random variables or two continuous random variables. It is a set in which they take values jointly. Okay. But otherwise you still have the joint PDF exactly defined the same way. So this omega xy becomes this region of support for, what do you understand by this region of support? What is the meaning of this idea for fxy? Like you had the interval omega, in the 1D case you would talk of capital omega x being the interval of support. So here you have a region of support, that is the only region where this has non-zero values. So if you take xy outside this region of support, you guarantee that fxy is 0. Right. So we will use this this nomenclature quite frequently. So okay. So what is the limitation of, okay, so this is, remember the bottom line is that, right, fxy, use of fxy is only one way of assigning, of consistently assigning probabilities, right. But note that we have to assign P to regions, otherwise we are not, right, dealing with two random variables, right. So, and it turns out that it is the most, right, analytically one of the simplest way, the easiest way of doing so, because these double integrals, even if you cannot evaluate them analytically, you can always evaluate them numerically and so on and so forth, right, and right, and so on, right. And we saw the other day also that the joint CDF is, which is defined specifically with this particular infinite, semi-infinite rectangle. In general, that is very complicated to compute and specify for each xy. So we will avoid that completely, even though it is put in all books as the holy grail, right. Everything starts off with joint CDF, but we will not take that approach here. Given that very few examples later on will anyway, nobody uses that joint CDF after stating it, aha, yes, it is there, and then people come away from that and only look at this. So, so we can avoid it right from the beginning, but just keep it in mind, in case somebody asks you the joint CDF, you should know how to answer them. So, so most general is joint CDF. This is by virtue of being a probability, it is bounded, it is always between 0 and 1, unlike this, which can take any real number, any positive real number. Okay. So anyway, so what are the limitations of using this joint PDF fx small f? It turns out that you cannot give positive probability to what types of entities in the plane. You cannot give positive probability to points, of course you cannot give positive probability beyond points. You cannot give probabilities to lines and curves. So the use of fxy means that, right, lines such as x equal to y, or in general curves, how do we define a general curve? G of x, well, let me write small x equal to y, right, instead of this, just to curves like g of xy equal to 0 always have 0 probability in, if you say that, if you start off with this. This is a very important point, so please pay attention. Again, this is a question which can come at you, so you should immediately say if you start with the by integrating a joint PDF like fxy, every curve has 0 probability. Why does it have 0 probability? Because it has 0 area. So by virtue of having 0 area, when you do this double integral over a region which has 0 area, which is a degenerate case of such a double integral, you know that the value has to be 0, isn't it? If this is a well behaved integrable function, right, if you cannot integrate it over a line and get finite answers. So the use of fxy means this: any line, in particular therefore, what does it mean for the probability that x will be equal to y? That has to be 0, because this line represents the event that capital X equal to y, capital Y. The event capital X equal to capital Y is captured by the line x equal to y, exactly as in the discrete case, isn't it? So which i.e. you say that P of x equal to y is 0 i.e. or e.g. whatever you want to say. Whereas okay, that's also true for any curve gxy. If you have the case that a very important special case which we will have to look at later with using some different tools is the same thing that we did. Maybe we didn't do it in such a great extent with discrete random variables, but we have the case of y being a function of x, right? So if y is a function of x, actually you don't need two random variables to describe that situation, because x is, let's say, a single random variable defined on some interval omega x, and knowing x, if you know y exactly, that happens when y equals fx, some function of x. Now I shouldn't use the word f or let f, but some g of x, whatever, right? It turns out that the entire probability is concentrated where? On the curve in which defines the two random variables, isn't it? Or the two variables in this case, just x, y and x. So that we will defer to a later discussion. Right? The important special case of y equal to, call it g of x, we will do different. I think you may have seen such cases in the other course, I am not sure, but anyhow, right? The case of y equal to g of x to be done later, right? This is too important a situation to pass up. But one thing remember, if y is g of x, that means your entire probability is concentrated in this line. There is no probability, by what happens here, omega xy automatically a zero area. So all probability is concentrated here, is on this line, or this curve, shall we say, in general, right? It could be over some interval, whatever. So here you cannot talk in this, right, in that situation you cannot ask or talk meaningfully of a joint PDF. Okay, so for now we are sticking to the case, right, of this very important equation here, where we are using the joint PDF, where we have a healthy joint PDF, a healthy non-zero region omega xy, and we are going to assign probabilities based on this very important relationship.